Precision versus Accuracy in Risk-Based Inspection, RBI, API RP 580, Understanding Measurement Quality in Inspection Processes. Introduction to Precision and Accuracy in RBI, Why Precision and Accuracy Matter in RBI, Accuracy, Definition and Engineering Meaning, Precision, Definition and Engineering Meaning, Precision versus Accuracy, Key Differences, Visual Interpretation of Accuracy and Precision, Components of Precision in Inspection Data, Impact of Precision and Accuracy on RBI Results. Examples affecting accuracy and precision in RBI, Engineering Best Practices and Conclusion. Risk-based inspection, RBI, is a structured methodology used in the oil, gas, petrochemical, and process industries to prioritize inspection activities based on risk, which is defined as the combination of probability of failure and consequence of failure. In this context, the concepts of precision and accuracy are fundamental because RBI relies heavily on inspection data, degradation rates, operating conditions, and damage models to make engineering decisions. Precision and accuracy directly influence the reliability of inspection results, corrosion rate calculations, remaining life estimates, and ultimately the risk ranking of equipment. According to API recommended practices updated through 580. Particularly API RP 581 and related RBI guidance, the quality of input data is one of the dominant factors affecting the credibility of RBI outputs. Precision refers to the consistency or repeatability of measurements, while accuracy refers to how close those measurements are to the true or actual condition of the equipment. An RBI program that produces highly precise but inaccurate data may consistently lead engineers to the wrong conclusions, whereas accurate but imprecise data can introduce high uncertainty and variability in risk estimates. This introductory slide establishes why understanding and managing both precision and accuracy is essential for sound engineering judgment. Regulatory compliance, and safe, cost-effective inspection planning. It also sets the foundation for discussing how API guidance addresses data uncertainty and how inspection engineers should interpret and manage measurement quality within RBI studies. Precision and accuracy matter in RBI because inspection and operational data form the backbone of risk calculations. RBI assessments use measured wall thickness, corrosion rates, crack sizes, operating pressures, temperatures, and material properties to estimate probability of failure. If measurements are inaccurate due to systematic bias, such as poor calibration or inappropriate inspection techniques, the calculated probability of failure may be significantly overestimated or underestimated. This can lead to either unnecessary inspections and costs or, more critically, insufficient inspection coverage and increased risk of failure. Precision, on the other hand, affects the confidence engineers have in trends and repeatability. Highly variable inspection results reduce confidence in corrosion rate calculations and make it difficult to distinguish real degradation from measurement noise. API guidance emphasizes that uncertainty in input data propagates through RBI models and directly affects risk outputs. In quantitative and semi-quantitative RBI, poor precision increases statistical uncertainty, while poor accuracy introduces bias. Both issues can distort risk ranking, inspection intervals, and mitigation decisions. Therefore, understanding and managing these two concepts is not academic but a practical necessity for maintaining mechanical integrity, ensuring safety, and optimizing inspection resources in accordance with API recommended practices. Accuracy is defined as the closeness of a measured or calculated value to the true or actual value. In engineering terms, accuracy is primarily affected by systematic errors or bias. Examples include incorrect calibration of ultrasonic thickness gauges, inappropriate corrosion models, incorrect material property assumptions, or using inspection methods that are not suitable for the damage mechanism present. Within the context of RBI as described in API guidance, accuracy reflects how well inspection data and analytical models represent the real condition of equipment. An accurate inspection result means that, on average, the reported thickness, flaw size, or damage extent is close to the actual condition. Even if some variability exists between individual measurements. Accuracy is particularly critical when determining remaining life, minimum required thickness, and probability of failure. Systematic inaccuracies can consistently skew RBI results in one direction, leading to flawed risk assessments across an entire system or facility. AP emphasizes the need for validated methodologies, appropriate inspection techniques, and proper calibration to improve accuracy and reduce bias in RBI inputs. Precision refers to the closeness of repeated measurements to each other under the same conditions. In RBI, precision is associated with random error and variability rather than bias. Highly precise measurements show little scatter and are repeatable, even if they are not necessarily accurate. Precision is influenced by factors such as instrument resolution, surface condition, inspector technique, data collection procedures, and environmental conditions during inspection. From an RBI perspective, precision affects the reliability of trends, such as corrosion rate calculations derived from multiple inspection campaigns. If measurements lack precision, it becomes difficult to distinguish true degradation from measurement noise, which increases uncertainty in probability of failure estimates. API guidance recognizes that while precision alone does not guarantee correctness, it is essential for reproducibility and confidence in RBI analyses, especially when comparing inspection results over time or across similar equipment. High precision supports consistent risk ranking and more defensible inspection planning decisions. The key difference between precision and accuracy lies in consistency versus correctness. Accuracy measures how close a result is to the true value, while precision measures how consistently that result can be repeated. In RBI applications, it is possible to have precise but inaccurate data, such as consistently underestimating wall thickness due to calibration bias. Conversely, data can be accurate on average but imprecise, showing large scatter that complicates trend analysis. API guidance implicitly addresses this distinction by emphasizing both data quality and uncertainty management. For RBI to be credible, inspection data must be both sufficiently accurate to reflect real equipment condition and sufficiently precise to support repeatable, defensible risk calculations. Understanding this distinction helps engineers interpret inspection results correctly, challenge questionable data, and apply appropriate safety factors or uncertainty adjustments in RBI models. Visual representations, such as target diagrams, are commonly used in engineering training to illustrate the relationship between accuracy and precision. In the context of RBI, these visuals help inspectors and engineers quickly grasp how measurement quality affects decision-making. An accurate and precise result would be analogous to measurements tightly clustered around the true damage state, providing high confidence in RBI outcomes. Precise but inaccurate results represent consistent but biased measurements, which can systematically mislead risk assessments. Accurate but imprecise results indicate that while the average condition may be correct, high variability increases uncertainty and reduces confidence. Finally, results that are neither accurate nor precise represent poor data quality and should not be relied upon for RBI decisions. Such visual interpretations reinforce API's emphasis on understanding uncertainty and avoiding blind reliance on inspection numbers without considering their quality. Precision in inspection data can be further divided into repeatability and reproducibility. Repeatability refers to the consistency of measurements taken by the same inspector using the same equipment under the same conditions. Reproducibility refers to consistency between different inspectors, equipment, or inspection campaigns. In RBI programs, poor repeatability may indicate instrument issues or inadequate procedures, while poor reproducibility often points to differences in technician skill, interpretation, or inspection setup. API guidance highlights the importance of standardized procedures, qualified personnel, and training to improve both aspects of precision. Improving precision reduces random error, enhances confidence in corrosion trends, and supports more stable and defensible RBI outcomes. Precision and accuracy directly influence the outputs of RBI analyses, including probability of failure, consequence assessment, and inspection interval determination. In quantitative and semi-quantitative RBI, highly precise data improves statistical confidence but does not correct for systematic bias. Conversely, accurate but imprecise data increases uncertainty ranges and may require conservative assumptions. API RP581, widely used for RBI, is designed to be reproducible and structured, but it still depends on the quality of input data. Measurement error and uncertainty propagate through damage models and risk calculations, affecting risk ranking and inspection prioritization. Understanding these impacts allows engineers to interpret RBI results appropriately, apply uncertainty factors, and avoid overconfidence in seemingly precise numbers. Several practical factors influence accuracy and precision in RBI applications. The selection of inspection methods, such as ultrasonic testing versus radiography, affects both bias and variability depending on the damage mechanism. Sensor calibration and drift can introduce systematic inaccuracies if not properly managed. Technician qualification, experience, and adherence to procedures strongly influence precision and reproducibility. Data handling, rounding, and interpretation during RBI studies can further affect results. API guidance stresses that these factors should be considered during data validation and RBI reviews to ensure that inspection data supports reliable risk-based decisions. Engineering best practices for RBI, as aligned with API recommended practices, focus on balancing and improving both precision and accuracy. This includes using validated and appropriate inspection techniques, maintaining calibration and quality control, applying competent and qualified personnel, and critically reviewing data for bias and variability. Engineers should explicitly consider uncertainty when interpreting RBI results and avoid relying solely on numerical outputs without engineering judgment. In conclusion, precision and accuracy are not competing concepts but complementary requirements for credible RBI. A well-designed RBI program recognizes their differences, manages their limitations, and uses them together to support safe, reliable, and cost-effective inspection planning.